In the previous video, we treated the color map as a texture using texture coordinates, which were mapped onto the surface of a 3D object. This video will explore an alternative color map approach based on vertex coloring, where color information is directly added to the vertices of the 3D model. Color map based on vertex coloring results in a more uniform appearance across the model's surface. This approach is simpler and requires fewer data, making it suitable for scenarios where texture coordinates are unavailable for certain 3D models obtained from the STL or OBJ files. Hello everyone. Welcome to my YouTube channel, Practical Programming with Dr. Sue. In the examples presented in the previous videos, a distinct texture containing the color map data was created. The texture coordinates were then assigned to each vertex of the object, which determine how the colors from the texture map onto the object's surface. The use of a color map as a texture facilitates detailed and realistic coloring of the object's surface, especially when dealing with complex patterns, images, or gradients. Color map can be added to built-in objects as a texture since these objects already contain UV coordinates within the scene. However, this approach has a disadvantage. It requires assigning texture coordinates to each vertex, which can be challenging for complex or dynamically changing geometries. Furthermore, texture-based color map consumes GPU memory, and the use of large textures or multiple textures can impact performance and memory usage. For complex 3D objects, people typically use specific packages such as Blender or Maya to create 3D models, which are then exported in various file formats such as STL, OBJ, etc. Various rendering engines, including PyGFX, can load these files to generate geometries for 3D objects. Nevertheless, some 3D file formats only provide geometry data. For example, the STL format, primarily designed for 3D printing, describes a 3D object's surface as a collection of triangular meshes, but doesn't provide a way to store additional information like UV coordinates and material properties. The famous teapot object discussed in our previous videos was created using the STL file and lacks texture coordinate data. Consequently, color map cannot be added as a texture to this teapot. To address this issue, this video will explain an alternative color map approach based on vertex coloring. In this approach, color map information is directly added to the vertex color attribute. Each vertex is assigned a color value corresponding to the color in the color map. As an illustration, consider a triangle with vertex coloring. For the first vertex positioned at 0, 0.5, 0, a red color is assigned. For the second vertex positioned at -0.5, -0.5, 0, a green color is assigned, while for the third vertex positioned at 0.5, -0.5, 0, a blue color is assigned. In the PyGFX engine, vertex colors are interpolated across this triangle during rasterization, resulting in a smooth color transition from vertex to vertex. The advantage of this approach is simplicity. It simplifies the process as it doesn't require texture coordinates. Color information is directly associated with vertices. Another advantage is resource efficiency because it doesn't require additional texture memory, making it more memory efficient for simple color assignments. Now, let's incorporate a color map based on vertex coloring into the teapot object. To utilize the previously created color map data for vertex coloring, we must devise a method to interpolate the data. In the color map data, we assume that the 11 color arrays from index 0 to 10 for each color map are uniformly distributed within the range of 0 and 1. For instance, the 0 element in the array represents a color at 0, and the 5th element represents a color at 0.5. However, if we aim to obtain a color at an arbitrary location, such as 0.55, we need to employ an interpolation method. Now, let's implement this color interpolation in the colormapdata.py file. Open this file from the common folder and add a new function called lerp. Here is the code for this function. It accepts color map data and an argument t whose value is in the range of min and max. This function enables you to interpolate a color for an arbitrary t value. Within the function, we first ensure the input t parameter is within the range of min and max. Next, we normalize the t variable to the range of 0 and 1, and finally, interpolate the color for the t variable. The function returns an array RGB with each color component being in the range of 0 and 1. With the lerp color function in place, we also need to code certain utility functions. Open the helper.py file from the common folder and add a new function called teapot geometry with this code. This function loads a 3D teapot model from a STL file, applies a rotation and translation to adjust its orientation and position, and then converts it into a geometry object. The TriMesh library is used for loading and manipulating the 3D model, and the resulting geometry is suitable for visualization with the PyGFX rendering engine. The purpose of this function is to position the teapot object to the center of the scene with a proper orientation for a better view. Subsequently, add another utility function named createVertexColorMap with this code snippet. This function takes a 3D geometry, a color map name, and a color map direction as its input arguments. It generates vertex colors for the geometry based on the color map and the specified direction. Within the function, we extract the position data of the 3D geometry and determine the range along the specified direction using the bounding box feature provided by the PyGFX engine. We then iterate over each position in the geometry, compute a color value linear interpolation using the lerp function implemented previously in the color map data file, based on the position and the determined data range. The resulting colors are stored in a list and then converted to a number Py array of type float, 32. The function finally returns the resulting colors as a number Py array. Now, we are ready to add color map to our teapot object with vertex coloring. Let's create a Python file named colormapteapot.py to the src/video_05 folder. In this file, we first import relevant modules, including PyGFX engine and Python linear algebra library, and then import the helper module from the common folder. Subsequently, we create an empty scene used to hold our background, objects, lights, and camera. Next, we define two color map parameters, the color map direction and color map name. In this case, the color map direction can take three values, 0, 1, and 2, corresponding the x, y, and z directions, respectively. This is different from the example in the previous video, where it can only take two values, 0 and 1, corresponding u and v directions in the texture coordinate system. Here, we set it to 1, meaning that the default color map is along the y direction. We also set the jet as the default color map name. To proceed, we define a function named getGeometry with optional parameters. Inside this function, we generate the geometry for the teapot and optionally set attributes based on keyword arguments. We then define two more functions, WObject class and material class. The WObject class is used to create a 3D mesh with the provided geometry and material, while the material class is used to create a Phong material for the mesh with optional parameters. In the following code, we create a geometry without arguments and use it to generate the vertex color by calling the createVertexColorMap function implemented previously in the helper module. Subsequently, we generate a 3D object with the specified geometry and material. Here, we pass the color map data to the geometry using the GFXBuffer function and set the material's color mode to vertex, indicating that we'll use the geometry colors buffer with one color per vertex to add the color map to the object. Additionally, we add a perspective camera and lights to the scene. We also define an animate function to rotate the object. Finally, we call the GFXShow function to render our teapot. Running this example creates a teapot with a color map on your screen, as shown here. Of course, we can add keyboard interaction as we did in the previous video for easily changing the color map name and color map direction. Here's the code for adding keyboard interaction. Since the code for keyboard interaction is similar to what we used in the previous video, we'll not go into the details and will only indicate the difference from the example in the previous video. In the previous example, by altering the color map or color map direction, we only need to change the materials or geometry's attributes. As shown here, when we change the color map, we need to regenerate the color map texture and assign it to the materials map attribute. On the other hand, as we change the color map direction, we only need to reset the geometry's texture coordinates. However, in our current example, when changing the color map name or color map direction, we need not only to regenerate the vertex color, but also to regenerate the object itself. In this case, we have to remove the old object from the scene and add the newly created object to the scene. To avoid code duplication, we use an additional Boolean variable called dataChange to check whether the color map name or color map direction has changed or not. If yes, we need to regenerate the object. Here demonstrates the result on the screen. Now, you can use the space key to change the color map direction, the up arrow key to change the color map name, and down arrow key to change the color map name in reverse order. In the same way, you can download 3D models from internet or create your own 3D models using Blender or Maya, and then add color map to these 3D models based on vertex coloring as we did here. Now is our showcase time. We'll place several 3D models from internet with color maps in different CubeMap skybox environments. Here are some examples, which demonstrate a more appealing visual effect is generated with the color map using vertex coloring.